Hello, biology students, and welcome to your very first video in a long series of interesting and quirky intellectual sessions. My name is Miss Hoskins, and this first video is on the nature of science. It's basically how we gather, communicate, and analyze information as scientists. Like most humans, I found myself naturally curious about the world at a younger age, always asking questions about why things were. I feel like science just fills my heart with wonder of our natural world. I always used to ask myself questions like, have you ever heard of Rockefeller Forest out in California and Washington State? They have the largest trees on our planet, the giant sequoia and of course the giant redwoods. The redwood trees grow to 379 feet high, and although that sounds amazingly huge, and you can find pictures online of people driving their cars through the trees, why 379 feet? Why not 500 feet? Why not 250 feet? That's pretty tall for a tree. Why did nature grow to 379 feet? How about this? Gastropods, part of the molluscus family, are very, very beautiful little creatures. You would walk up to any of those shells and think, if I found those inside of a river system, I would pick them up and keep them. They're definitely collectible and beautiful. However, the one on top, that guy, he lives in the freshwater system. He's beautiful, harmless. The one on the bottom, by the way, a cone snail, they actually shoot poisonous darts out of their body. Now, isn't that interesting? An animal that will shoot poisonous darts. It is a fearsome predator. And what was the function of T-Rex's little tiny little baby arms? I mean, the most fearsome predator on the entire planet only had 2 functional limbs. What were the function of those little tiny baby arms? And how about this? The world is full of wonder. Just ask any mother who's had a child who's made another human being with their own body. I find it fascinating how our bodies can heal themselves. Everything inside of our body, for the most part, can regenerate and healing. But we're born with all the teeth that we're ever going to have. It's true. Babies, when they are born, they have all these teeth just shoved up inside of their skulls. And as you develop, as you know, as teenagers, they fall out and they're replaced by adults. And as adults, we get that one set of teeth. That's it. For the majority of our life, we get the one set of teeth. How come we can regenerate all of these other things? Skins, cells, variety of things, immune system, blood. But yet, we're born with all the teeth that we're ever going to have because we need those our entire lifetime. That seems important to me. In order to investigate the nature of science, we have to come with a couple of terms. First, we have to know what a fact is. A fact is just some sort of objectable variable in something. In order for something to be a fact, it has to be relatively objective. Water boils at 100 degrees Celsius. There's nothing inquisitive or investigative about it. It's just we know that that's the temperature at which water goes from a liquid to a gas. Something is a principle when it's a statement that we know is based on repeated experimental observations, like the greenhouse effect. We know that we have a planet, and the planet has, trees and people, and then there's, of course, what we call our ozone layer. It's oxygen, and it keeps our planet warm. The reason for that is that there's the sun, and the sun has rays, and these rays, which you'll learn more about a lot of this later, enter between our ozone layer, and this bounces around, keeping our planet warm. And that's based on so much observation that we call that a principle. There's a principle of the greenhouse effect. If we take a principle of something and broaden its concept, it becomes a law, and the law describes that principle. We find that laws have patterns in nature, and they're oftentimes become accepted as facts, like Newton's laws of motion. Newton had 3 laws of motion, you may know. For every action, there's an equal and opposite reaction. I won't go through all of them, but Newton's laws are referred to that as such because they become very, very acceptable and they're basically the foundation of other fields of science. Other things are like Boyle's gas laws or the law of conservation of mass. Matter's not created nor destroyed, only transformed. Something becomes a theory when it's the explanation of this particular phenomenon. Scientists will often organize facts and research them to great length to form an explanation of why something happens. And when it becomes accepted by our scientific community, in terms we call it a theory. Oftentimes students mistake the meaning of that word because you spend a lot of time in literature classes going over what do you think the author was thinking, and the term is often misused. As a scientist, a theory will never become a fact or a law. It will become an observable explanation. You have to understand that science is based on experimentation. We conduct experiments in a process that is uniform to come up with new ways of understanding and a way to build upon new findings. There isn't really one way to design an experiment, but there is an investigative process that tends to follow like this general research pattern. Scientists often ask a question like, why does the T-Rex have those tiny little arms? You conduct as much background research as you can. What did other scientists or paleontologists think about those tiny little arms on T-Rex? Then you want to construct a hypothesis. Test it, design an experiment to test it. Once you gather that experimental data, let's analyze it, look at it objectively. What does it say? And then you want to communicate that to the scientific community, draw a conclusion, and put it out there for your other partners and people in our field to see. Sometimes more questions arise from these observations or conclusions. So an observation is basically a description of something. You can see something, smell it, touch it, taste it. It's not an opinion per se. Remember, science is very objective. Like when it rains, the ground is wet. That's an observation. You can make an inference about something, like maybe take a guess about what is going to happen based on your previous observations. Making an inference on a single observation is not always the case, but for some things that are simple enough, we can infer. Like if the ground is wet, then it rained. Or perhaps someone was watering plants. Pause the video for just a second and make an observation and then an inference about the photo. As an observation, you might have said, wow, the human all the way to the right has purple shorts, or the humans in the middle all have clothing that contains red in them. As an inference, you could have said something like, that must be Grandpa and his 4 grandkids coming back from Star Wars movie. Sometimes our observations, they can be qualitative or quantitative. Qualitative describes the qualities of something, like it's green, or it smells funny, smells sweet, could taste sour. Maybe it has a large hole, or it's longer than something else. Quantitative observations, they are actually using measurement. That is actually 4 feet long. I measured it. It was 7.2 grams, or 100 milliliters. Pause the video for just a second and see if you can say something qualitative and then quantitative about the image. You might have said quantitatively, there are 21 of those cookies. Qualitatively, based on the little girl's reaction to the cookies, you could have said something like, they must taste really, really good. Now, just as a thought, if we're going to make an inference, doesn't it seem like she took a bite of every single one of those cookies on the tray? Specifically, when we're looking at quantitative data that we can measure, we want to be as precise and accurate as we can. But there's value in both precision and accuracy. Precision can be how close your measurements are together. This is data that is very, very concise. It's specific. It's to an actual measurement of something. Or it can be accurate. That's how close you are to your measurement, how close you are to a correct or accepted value. For instance, take a look at these targets. The top left one, no doubt, that is precise and accurate. The top right one, however, has really good precision. Precision has value in science. It's not accurate, it missed the target, but precision tells us something about our experiment. If we're looking at this one right here, this target shows accuracy, but it's not precise. It hit the bullseye, sort of, but they're not close together. Not every data point fell within that particular accurate and precise range. And this one, of course, they're all over the place. It's neither accurate nor precise.